Welcome back to Fractal Aerodynamics. My name is Felix Schaller and I am the host of this channel. This is a short teaser of our upcoming test where we can show or we can make a certain proof of effect what happens inside constricted tubes. So we have here a tube system that is wide at the beginning and has a certain flow speed, and it is constricted in the middle where the flow is accelerated, and by that we know that the pressure is dropping inside accelerated fluid parts, but shall rise again in the diffuser part where the fluid is slowed down to its original speed. This is a claim that came up in the earliest days of fluid dynamics, where people like Venturi claimed that there has to be an energy conservation inside this fluid, where the energy that is coming here has to be restored in this part. And therefore we have this relation between static pressure and dynamic pressure, but we will show that this is a kind of misinterpretation of fluid behavior, because there is not really a relation of potential fields, because potential fields is something that is like gravity or density or any kind of tension that it can store energy. But an incompressible fluid is not able to store energy, and by that the energy must come from somewhere else. So this test is about showing this correlation between inertia and static and dynamic pressure. Alright, I will show you this in action. Alright, we have water hose here that enters or changes the diameter, that goes into a flat shape, and then we have a wider flow that is narrowed here in this section. Then we have here a static pressure tube. This is a dynamic or a variable static pressure tube that can be narrowed to about 1 millimeter and widened about 30 millimeters. Then we have here again a static pressure tube that is indicating the pressure after the acceleration in the deaccelerated part of the diffuser, and then finally the water goes out here. So I will demonstrate it now how that is working. First we put it back to the narrow we put it back into the narrow state, and we will start it. I forgot. Here, this is a little dispersion color for walls, where we can see the stream. We can analyze it a bit, how it flows through this tube section. So let's give it a go. So as you can see, the entering pressure is too high, that it causes water levels that are above this level. Alright, I give it a bit of dispersion color so we can see the dispersion color coming. Again. But we have to lower it a bit. Water level is here. increase the diameter. Increase it a bit. Now this is up here. You can see it. Let's change the speed. All right. That's for now. What we have seen in the beginning is that the entering pressure is way higher, so I put some tissue inside to stop it from rinsing out of the pressure probe that is before the accelerated part, and what we could see is that the water levels were merely straight, and even at when the gap was smaller, the pressure in the constricted part was even higher than in the diffuser part. So we have to figure out what is the reason for the behavior, that there is a higher pressure inside the constricted part than in the diffuser part. Here this is obvious, but usually I should at least a bit of a higher pressure in the diffuser part. All right, that's for it. Stay tuned for the real chapter that is discussing it in a more deeper manner, and stay tuned, keep in touch, bye bye.